In combinatorics, a branch of mathematics, a matroid (METRD) is a structure that captures and generalizes the notion of linear independence in vector spaces. There are many equivalent ways to define a matroid, the most significant being in terms of independent sets, bases, circuits, closed sets or flats, closure operators, and rank functions. Matroid theory borrows extensively from the terminology of linear algebra and graph theory, largely because it is the abstraction of various notions of central importance in these fields. Matroids have found applications in geometry, topology, combinatorial optimization, network theory and coding theory. Definition: there are many equivalent ways to define a matroid. Independent sets in terms of independence. A finite matroid is a pair, whereas a finite set N is a family of subsets of with the following properties. The empty set is independent, i.e., alternatively, at least one subset of is independent, i.e., every subset of an independent set is independent, i.e., for each if-then. This is sometimes called the hereditary property. If an or two independent sets of N has more elements than, then there exists an element in that when added to gives a larger independent set than. This is sometimes called the augmentation property or the independent set exchange property. The first two properties define a combinatorial structure known as an independent system. Bases and circuits. A subset of the ground set that is not independent is called dependent. A maximal independent set, that is, an independent set which becomes dependent on adding any element of, is called a basis for the matroid. A circuit in a matroid is a minimal dependent subset of, that is, a dependent set to whose proper subsets are all independent. The terminology arises because the circuits of graphic matroids are cycles in the corresponding graphs. The dependent sets, the bases, or the circuits of a matroid characterize the matroid completely. A set is independent if and only if it is not dependent, if and only if it is a subset of a basis, and if and only if it does not contain a circuit. The collection of dependent sets, or of bases, or of circuits each has simple properties that may be taken as axioms for a matroid. For instance, one may define a matroid to be a pair, whereas a finite set is before and is a collection of subsets of called bases, with the following properties. Is non-empty. If and are distinct members of N, then there exists an element such that it follows from the basis exchange property that no member of can be a proper subset of another. Rank functions. It is a basic result of Matroid theory, directly analogous to a similar theorem of bases in linear algebra, that any two bases of a matroid have the same number of elements. This number is called the rank of. If is a matroid on, and is a subset of, then a matroid on can be defined by considering a subset of to be independent if and only if it is independent in. This allows us to talk about submatroids and about the rank of a subset of. The rank of a subset A is given by the rank function R of the matroid, which has the following properties. The value of the rank function is always a non-negative integer, for any subset of, for any two subsets N of, that is, the rank is a submodular function, for any set and element. From the first of these two inequalities it follows more generally that, if then, that is, the rank is a monotonic function. These properties can be used as one of the alternative definitions of a finite matroid. If satisfies these properties, then the independent sets of a matroid over can be defined as those subsets of with. The difference is called the nullity or core rank of the subset. It is the minimum number of elements that must be removed from to obtain an independent set. The nullity of N is called the nullity or core rank of. Closure operators. Let be a matroid on a finite set, with rank function as above. The closure of a subset of is the set. This defines a closure operator where denotes the power set, with the following properties. For all subsets IV, for all subsets IV, for all subsets N of with, for all elements, and of and all subsets of, if then. The first three of these properties are the defining properties of a closure operator. The fourth is sometimes called the Mac-Lane-Steinitz exchange property. These properties may be taken as another definition of matroid. Every function that obeys these properties determines a matroid. Flat A set whose closure equals itself is said to be closed, or a flat or subspace of the matroid. A set is closed if it is maximal for its rank, meaning that the addition of any other element to the set would increase the rank. The closed sets of a matroid are characterized by a covering partition property. The whole point set is closed. If and a flat, then is a flat. If is a flat, then the flats that cover partition the elements of the class of all flats, partially ordered by set inclusion, forms a matroid lattice. Conversely, every matroid lattice forms a matroid over its set of atoms under the following closure operator. For a set of atoms with join, the flats of this matroid correspond one for one with the elements of the lattice. The flat corresponding to lattice element is the set. Thus, the lattice of flats of this matroid is naturally isomorphic to hyperplanes in a matroid of rank. A flat of rank is called a hyperplane. These are the maximal proper flats, that is, the only superset of a hyperplane that is also a flat is the set of all the elements of the matroid. Hyperplanes are also called cotoms or copoints. An equivalent definition. A cotom is a subset of E that does not span M, but such that adding any other element to it does make a spanning set. The family of hyperplanes of a matroid has the following properties, which may be taken as yet another axiomatization of matroids. There do not exist distinct sets unin with, that is, the hyperplanes form a Sperner family. For every indistinct with, there exists with. Examples. Uniform matroids let E be a finite set and K a natural number. One may define a matroid on E by taking every K element subset of E to be a basis. This is known as the uniform matroid of rank K. A uniform matroid with rank K and with n elements is denoted. All uniform matroids of rank at least 2 are simple. The uniform matroid of rank 2 on n points is called the n-point line. A matroid is uniform if and only if it has no circuits of size less than the 1 plus the rank of the matroid. The direct sums of uniform matroids are called partition matroids. In the uniform matroid, every element is a loop, and in the uniform matroid, every element is a coloop. The direct sum of matroids of these two types is a partition matroid in which every element is a loop or a coloop. It is called a discrete matroid. An equivalent definition of a discrete matroid is a matroid in which every proper, non-empty subset of the ground set E is a separator. Matroids from linear algebra. Matroid theory developed mainly out of a deep examination of the properties of independence and dimension in vector spaces. There are two ways to present the matroids defined in this way. If E is any finite subset of a vector space V, then we can define a matroid M on E by taking the independent sets of M to be the linearly independent subsets of E. The validity of the independent set axioms for this matroid follows from the Steinitz exchange lemma. If M is a matroid that can be defined in this way, we say the set E represents M. Matroids of this kind are called vector matroids. An important example of a matroid defined in this way is the Fano matroid, a rank 3 matroid derived from the Fano plane, a finite geometry with 7 points and 7 lines. It is a linear matroid whose elements may be described as the 7 non-zero points in a three-dimensional vector space over the finite field GF. However, it is not possible to provide a similar representation for the Fano matroid using the real numbers in place of GF. A matrix A with entries in a field gives rise to a matroid M on its set of columns. The dependent sets of columns in the matroid are those that are linearly dependent as vectors. This matroid is called the column matroid of A, and A is said to represent M. For instance, the Fano matroid can be represented in this way as a 3 times 7 matrix. Column matroids are just vector matroids under another name, but there are often reasons to favor the matrix representation. A matroid that is equivalent to a vector matroid, although it may be presented differently, is called representable or linear. If M is equivalent to a vector matroid over a field F, then we say M is representable over F. In particular, M is real representable if it is representable over the real numbers. For instance, although a graphic matroid is presented in terms of a graph, it is also representable by vectors over any field. A basic problem in matroid theory is to characterize the matroids that may be represented over a given field F. Rota's conjecture describes a possible characterization for every finite field. The main results so far are characterizations of binary matroids, due to Tutt, of ternary matroids due to Reed and Bixby, and separately to Seymour, and of quaternary matroids due to Gielen, Gerards, and Kapur. This is very much an open area. A regular matroid is a matroid that is representable over all possible fields. The Vamos matroid is the simplest example of a matroid that is not representable over any field. Matroids from graph theory. A second original source for the theory of matroids is graph theory. Every finite graph G gives rise to a matroid M as follows. Take as E the set of all edges in G and consider a set of edges independent if and only if it is a forest, that is, if it does not contain a simple cycle. Then M is called a cycle matroid. Matroids derived in this way are graphic matroids. Not every matroid is graphic, but all matroids on three elements are graphic. Every graphic matroid is regular. Other matroids on graphs were discovered subsequently. The bicircular matroid of a graph is defined by calling a set of edges independent if every connected subset contains at most one cycle. In any directed or undirected graph G, let E and F be two distinguished sets of vertices. In the set E, define a subset U to be independent if there are U vertex disjoint paths from F onto U. This defines a matroid on E called a gamoid. A strict gamoid is one for which the set E is the whole vertex set of G. In a bipartite graph G equals 1 may form a matroid in which the elements are vertices on one side U of the bipartition, and the independent subsets are sets of endpoints of matchings of the graph. This is called a transversal matroid, and it is a special case of a gamoid. The transversal matroids are the dual matroids to the strict gamoids. Graphic matroids have been generalized to matroids from signed graphs, gain graphs, and biased graphs. A graph G with a distinguished linear class B of cycles, known as a biased graph, has two matroids, known as the frame matroid and the lift matroid of the biased graph. If every cycle belongs to the distinguished class, these matroids coincide with the cycle matroid of G. If no cycle is distinguished, the frame matroid is the bicircular matroid of G. A signed graph, whose edges are labeled by signs, and a gain graph, which is a graph whose edges are labeled orientably from a group. Each give rise to a biased graph and therefore have frame and lift matroids. The Lehmann graphs form the basis of the two-dimensional rigidity matroid, a matroid defined in the theory of structural rigidity. Let G be a connected graph and E be its edge set. Let I be the collection of subsets F of E such that G minus F is still connected. Then is a matroid, called bond matroid of G. Note that the rank function R is the number of minimal cycles in a subgraph induced on the edge subset F. Matroids from field extensions. A third original source of matroid theory is field theory. An extension of a field gives rise to a matroid. Suppose F and K are fields with K containing F. Let E be any finite subset of K. Define a subset S of E to be algebraically independent if the extension field F has transcendence degree equal to S. A matroid that is equivalent to a matroid of this kind is called an algebraic matroid. The problem of characterizing algebraic matroids is extremely difficult. Little is known about it. The Vamos matroid provides an example of a matroid that is not algebraic. Basic constructions. There are some standard ways to make new matroids out of old ones. Duality. If M is a finite matroid, we can define the orthogonal or dual matroid M** by taking the same underlying set and calling a set a basis in M** if and only if its complement is a basis in M. It is not difficult to verify that M** is a matroid and that the dual of M** is M. The dual can be described equally well in terms of other ways to define a matroid. For instance, a set is independent in M** if and only if its complement spans M. A set is a circuit of M** if and only if its complement is a coterm in M. The rank function of the dual is, according to a matroid version of Kuratowski's theorem, the dual of a graphic matroid M is a graphic matroid if and only if M is the matroid of a planar graph. In this case, the dual of M is the matroid of the dual graph of G. The dual of a vector matroid representable over a particular field F is also representable over F. The dual of a transversal matroid is a strict gammoid and vice versa. Example: the cycle matroid of a graph is the dual matroid of its bond matroid. Minus if M is a matroid with element set E, and S is a subset of E, the restriction of M to S, written M, S, is the matroid on the set S whose independent sets are the independent sets of M that are contained in S. Its circuits are the circuits of M that are contained in S, and its rank function is that of M restricted to subsets of S. In linear algebra, this corresponds to restricting to the subspace generated by the vectors in S. Equivalently, if D equals M minus S, this may be termed the deletion of T, written MT or M minus T. The submatroids of M are precisely the results of a sequence of deletions. The order is irrelevant. The dual operation of restriction is contraction. If T is a subset of E, the contraction of M by T, written MT, is the matroid on the underlying set E minus T whose rank function is in linear algebra. A matroid N that is obtained from M by a sequence of restriction and contraction operations is called a minor of M. We say M contains N as a minor. Many important families of matroids may be characterized by the minor minimal matroids that do not belong to the family. These are called forbidden or excluded minors. Sums and unions. Let M be a matroid with an underlying set of elements E, and let N be another matroid on an underlying set F. The direct sum of matroids M and N is the matroid whose underlying set is the disjoint union of E and F, and whose independent sets are the disjoint unions of an independent set of M with an independent set of N. The union of M and N is the matroid whose underlying set is the union of E and F, and whose independent sets are those subsets which are the union of an independent set in M and one in N. Usually the term union is applied when E equals F, but that assumption is not essential. If E and F are disjoint, the union is the direct sum. Additional terminology. Let M be a matroid with an underlying set of elements E. E may be called the ground set of M. Its elements may be called the points of M. A subset of E spans M if its closure is E. A set is said to span a closed set K if its closure is K. The girth of a matroid is the size of its smallest circuit or dependent set. An element that forms a single-element circuit of M is called a loop. Equivalently, an element is a loop if it belongs to no basis. An element that belongs to no circuit is called a coloop or isthmus. Equivalently, an element is a coloop if it belongs to every basis. Loop and coloops are mutually dual. If a two-element set F, G, is a circuit of M, then F and G are parallel in M. A matroid is called simple if it has no circuits consisting of one or two elements. That is, it has no loops and no parallel elements. The term combinatorial geometry is also used. A simple matroid obtained from another matroid M by deleting all loops and deleting one element from each two-element circuit until number two element circuits remain is called a simplification of M. A matroid is co-simple if its dual matroid is simple. A union of circuits is sometimes called a cycle of M. A cycle is therefore the complement of a flat of the dual matroid. A separator of M is a subset S of E such that a proper or non-trivial separator is a separator that is neither E nor the empty set. An irreducible separator is a separator that contains no other non-empty separator. The irreducible separators partition the ground set E. A matroid which cannot be written as the direct sum of two non-empty matroids, or equivalently which has no proper separators, is called connected or irreducible. A matroid is connected if and only if its dual is connected. A maximal irreducible submatroid of M is called a component of M. A component is the restriction of M to an irreducible separator, and contrariwise, the restriction of M to an irreducible separator is a component. A separator is a union of components. A matroid M is called a frame matroid if it, or a matroid that contains it, has a basis such that all the points of M are contained in the lines that join pairs of basis elements. A matroid is called a paving matroid if all of its circuits have size at least equal to its rank. The matroid polytope is the convex hull of the indicator vectors of the bases if. Then a matroid on can be defined by considering a subset of to be independent if and only if it is independent in. This allows us to talk about submatroids and about the rank of a subset if. The rank of a subset A is given by the rank function R of the matroid, which has the following properties. The value of the rank function is always a non-negative integer, for any subset if, for any two subsets and of, that is, the rank is a submodular function, for any set and element. From the first of these two inequalities it follows more generally that, if then, that is, the rank is a monotonic function. These properties can be used as one of the alternative definitions of a finite matroid. If satisfies these properties, then the independent. There are many equivalent ways to define a matroid. Independent sets in terms of independence. A finite matroid is a pair, whereas a finite set N is a family of subsets of with the following properties. The empty set is independent, i.e., alternatively, at least one subset of is independent, i.e., every subset of an independent set is independent, i.e., for each, if then. This is sometimes called the hereditary property. If an or two independent sets of N has more elements than, then there exists an element in that when added to gives a larger independent set than. This is sometimes called the augmentation property or the independent set exchange property. The first two properties define a combinatorial structure known as an independence system. Bases and circuits. A subset of the ground set that is not independent is called dependent. A maximal independent set, that is, an independent set which becomes dependent on adding any element of, is called a basis for the matroid. A circuit in a matroid is a minimal dependent subset of, that is, a dependent set to whose proper subsets are all independent. The terminology arises because the circuits of graphic matroids are cycles in the corresponding graphs. The dependent sets, the bases, or the circuits of a matroid characterize the matroid completely. A set is independent if and only if it is not dependent, if and only if it is a subset of a basis, and if and only if it does not contain a circuit. The collection of dependent sets, or of bases, or of circuits each has simple properties that may be taken as axioms for a matroid. For instance, one may define a matroid to be a pair, whereas a finite set is before and is a collection of subsets of called bases, with the following properties. Is non-empty. If and are distinct members of N, then there exists an element such that it follows from the basis exchange property that no member of can be a proper subset of another. Rank functions. It is a basic result of Matroid theory, directly analogous to a similar theorem of bases in linear algebra, that any two bases of a matroid have the same number of elements. This number is called the rank of. If is a matroid on, and is a subset if. In combinatorics, a branch of mathematics, A matroid (METRD) is a structure that captures and generalizes the notion of linear independence in vector spaces. There are many equivalent ways to define a matroid, the most significant being in terms of independent sets, spaces, circuits, closed sets or flats, closure operators, and rank functions. Matroid theory borrows extensively from the terminology of linear algebra and graph theory, largely because it is the abstraction of various notions of central importance in these fields. Matroids have found applications in geometry, topology, combinatorial optimization, network theory and coding theory. Definition: